Okay, so good day, everybody. That was a great introduction. Some technical issues. I hope you are all well and healthy. And yeah, I'm Marcel. I'm a principal data scientist at the ETH Zurich at the Swiss Data Science Center. And if you are looking for help to leverage your full potential in data science project, just reach out to me. But today I will not talk about data science or artificial intelligence or machine learning. Today I'm going to talk about astrophotography and yeah, what kind of frustration you can face when you do that hobby, but why it's still worth to keep going. So let me start by a small story. So quite a while back, I fell in love with physics and especially in astrophysics because I was interested in questions like what keeps a star shining, or how do planets form, or is it really true that we cannot travel faster than light? So most of those questions has been answered during my physics education in universities, but I started to have a dream. Namely, I wanted to have my own telescope to basically watch out the stars on my own, do my little experiments, and so on. So at that time, that was a dream, but of course, we all know what is the meaning of life. If you don't know what the meaning of life is, then just read here. So that's the meaning of life, right? Let dreams come true. So a few months ago, I decided to give it a go, and yeah, I wanted to buy the Hubble telescope, but NASA was not open for a deal, so I ended up with this setting here. I call it checkup. Before, basically, we talk about checkup and why he's up time to time a bit bitchy. Yeah, I basically will give you a bit more context and clear up some basics. So if you are in the business of astrophotography, you can go for many different things. For example, you could be interested in things like the structure of the moon's surface, or you can go for imaging planets in our solar system like Mars or Jupiter or Saturn, or you can go really, really big and you can try to make images from galaxies like this one here. This one is the Andromeda Galaxy, and Andromeda Galaxy is about 2.5 million kilometers light years away from the Earth. So this means that this image here has been taken a few months ago, and but it shows the galaxy in a state. It has been 2.5 million years in the past. I mean, that's just amazing, right? And that's because the light basically travels that long from Andromeda to the Earth and ends up at some point in a CCD camera like this one here, which I will explain you a bit later. So now let's just give a bit more context on what a galaxy is. So basically a galaxy is just a bunch of stars, right? And you need quite a lot of stars to make a galaxy. So you need more than 1,000, more than 100,000, more than a million. Basically, you need that much stars to make up a galaxy. So what's that number? This is about 100 billion stars. So you need about 100 billion stars to make an average galaxy like the galaxy we are living in, or the Andromeda Galaxy. So you can compare that number to the number of neurons humans have in their brains. Yeah, as we all know, there are some humans that have much less, but I think that's a completely different story. So let me tell you a tiny, tiny secret about stars. So did you ever wonder where all these atoms come from? Like the atoms which are basically, yeah, in your chair, when you sit on your chair, or in the device you are staring at, or the atoms that made you, or that made me. So where do they come from? Well, part of those atoms have been created during the Big Bang, And another big part has been created and is created all the time in stars. So let me explain that a bit. Let's take our sun, which is an ordinary star, right? The core temperature in our sun is about 14 million degrees. So that's hot enough that hydrogen fuses to helium, to a helium core. And during that process, energy is released. And this energy is, yeah, the light of the sun, lucky us. But at some point, the stock, basically, of hydrogen has gone, and the star basically starts to shrink. Basically, the core of the stars starts to shrink like this, or probably not exactly like this, but you get it. During that process, even heavier elements are created, like oxygen, carbon. Carbon is the fabric of our DNA. I mean, it's true that we are literally star stuff or stardust. So that's a scientific fact. I think it's a beautiful fact. So now, but let's forget about galaxies and stars and farting balloons at the moment. And let's talk about a bit the bitchy jackal here. So I want to explain what it takes, or what components do you need to make or to take an image from a galaxy. So I take you with me now. So I take the camera. I hope I do not destroy the technique again. Yeah, so I go around this telescope. I hope you see everything. So there is a tripod where everything is based on. You have the mount, basically, with the electronic to move the telescope. You have quite a heavy weights to balance the telescope. So the telescope is really balanced. So if I unlock it, basically, I can move it, right? So if each of those weights is 5 kilo, then of course you have the optical tube here, you have the whole image train. This is called image train. This is another optical element which reduces the focal length of the tube here. You have two cameras here. So this is the main camera, and this camera basically takes light from the object you want to take a picture, like a galaxy or a planet. It's a CCD camera. You can cool down this CCD camera to, let's say, minus 20 degrees to reduce the noise, thermal noise, and flow and stuff like that. Now this camera here, it's a little camera. This little camera basically takes care that the tracking of the whole system, so of course it basically follows the galaxy, because the Earth has a relative movement to the night sky, and this camera ensures that the telescope can closely follow the object you want to track. Then the optical tube, this is so-called Schmidt Casagrande telescope. It has two mirrors. So one mirror is here on the back side. This is the main mirror. So the light basically comes to this main mirror and then basically is reflected to a second mirror, which is up here. So let me take away this one. So, so here you have the second mirror, and basically the light is reflected on the second mirror as well, goes down, enters the optical train, and ends up here in that main camera. Now this telescope basically has 2 degrees of freedom, so you can basically move it in that direction, move it in that direction, and you have another degree of freedom which goes like that, right? The point is that, of course, when you follow or you track an object like a galaxy, you cannot move the telescope by hand, because you would basically lose the you use the object with time, so there is a little highly optimized motor here, engine, a little engine, and this little engine basically is connected via this hand controller here, where you can basically move your telescope with a computer, and in this computer basically you more or less control everything. So one thing, of course, is what you want to photograph here. So this is Andromeda again. And the other thing, for example, you control the camera here. So I can control the cooling of the camera. For example, I can say that I want to cool down the camera to, let's say, 0 degree in 8 minutes. I set it, and then the camera starts to cool down to, the main camera starts to cool down to -2 degrees in that case. Now there is a second program which is called PhD, and this program basically is connected with the small camera, where the small camera tries to fixate on a star and follow then basically based on the coordinates of that star the object you want to track. So there is a lot of electronics here. And this is basically more or less the setting you would have when you go out to the field and basically you want to take an image of a galaxy or a planet. Now, what can go wrong with this setting? Well, everything can go wrong, and every time you try to make an image of something, something will go wrong. And most of the time, many things simultaneously go wrong. So when you go outside and basically you stack the whole rig together, you have to do several things. First of all, you have to do a so-called polar alignment. That means that the optical axis here of this guy here, of the optical tube, has to be parallel to the axis of the Earth, rotational axis of the Earth. And like that, you can kind of cancel out the movement of the Earth relative to the night sky just by this degree of freedom here. Okay, and again, so the little camera is in charge that the motor and everything just moves the telescope in a way that you can follow the object you want to photograph. Now, to do that, to basically make it really aligned with the rotational axis of the Earth, is quite difficult in a sense that it has really to be accurate, and it can take several minutes. It can take up to an hour or two, depending on how good things work out. What can else be frustrating? Well, for example, the camera does not connect to the computer, or this camera does not connect to the computer, or as a pro like me, you forget to remove the cap over there, and then basically the computer and the program tells you that it found 100 stars to calibrate, but at the end, this is just thermal noise. What else can be frustrating? Frustrating can be, for example, that the whole computer program has some bugs, like every computer program, unexpected behavior. It's night, it's dark, so it's not always easy to manipulate everything. It can be that the battery is down. It can be that the cables are too long, the signals come not through, and so on. So that there are so many different things, basically, which can be. I put you back now. Okay. Hope you see me. Yeah, there can so many frustrating things be, but at the end, I think it's really worth to do it, because it teaches you a lot. At least it teaches me a lot. So Chekhov basically teaches me to be very patient and also, yeah, to work for a specific target, even if the target is challenging, then at the end, the journey is worth for all the work you have to do. So probably you wonder why didn't I show you an image? I did. Basically, I'm not yet there where I want to be to show images, so I'm not satisfied with the quality I reached so far. That's why the two images I showed you, the galaxy and the moon, are taken from a guy called Dylan O'Donnell from Australia, and another one, Corey Smith, just to give the right credits for those images. And I hope that I basically will be able to get a similar quality after a few more sessions of exercises. So yeah, more or less, I think I'm done. Just a few closing words. I think that it's worth to, let's say, that you look up more often to the night sky, right? Because I think it puts things a bit in a relation, and also I think that the Earth would be a more peaceful place when people would look up more often to the night sky. So I don't know if 15 minutes are over, but I think so. And yeah, I hope you enjoyed it.
Thank you so much, Marcel, for taking us on that journey, quite literally with the camera. I think that was a nice break from the slide decks we've seen before and probably will some more after. And yeah, we're looking forward to see some of your own pictures soon, hopefully.
Yeah.
Cool. Have a nice afternoon, and the audience, please stay tuned. In a few minutes, we'll be joined by Rena, who will tell us a little bit more about dealing with fast-changing plans. See you in a bit.